we're going to need one more fairly complicated result about totally bounded spaces in order to prove that complete and totally bounded is indeed enough to be compact. And this is the generalization of the Bolzano-Weierstrass theorem. Which you may recall from last semester. The Bolzano-Weierstrass theorem says if you've got a bounded sequence in the real numbers, then there is a convergent subsequence. What we're going to prove is that this is also true in any not necessarily in any totally bounded metric space. Being regular bounded is not enough, but being totally bounded is. And if you're also complete, and we're only going to prove that a Cauchy sequence exists, but of course, if you're also complete, meaning you're compact, then that's enough to show that you've got a convergent and subsequence. And then the idea is that if you've got any sequence then there is a not convergent but Cauchy subsequence. XNK. So let's prove this. And the first thing we're going to do is set up some notation. So because X is totally bounded, if M is a natural number, then 1 over M is a radius, so we're going to put it in so we're going to put that into our definition of total boundedness. So there is a finite number J sub M and points let's see, x1, x2 up through x sub J sub M such that X is contained in the union from J equals 1 up to J sub M, ball centered at X sub J of radius 1 over M. And then eventually I'm going to want to talk about, you know, you might get different points for different values of M, so we're going to have to use double subscripts, a J down below and an M upstairs. And then we're going to have our sequence xn and our subsequence xnk. I kind of don't want to use subscripts at this point. So let's let F sub M be this finite set, x1 sub M up through xm sub J sub M. then the things to remember are f sub m is finite, and x is contained in the union overall x in f sub m, ball centered at x of radius 1 over m. And now I want to be clear, let's use A to refer to our sequence of points, the things we're trying to show have a convergent subsequence. And we're going to use X to refer to the center of these balls in our definition of totally bounded. Now let's start building our subsequence. So here's the first thing I'm going to point out to you, is that the natural numbers, that is an infinite set. And our f1 is finite. And each k in the natural numbers satisfies a sub k has to be in the ball centered at x of radius 1 for some x in f1. So there is a particular x, let's call it x1 in our set f1, such that infinitely many points are in the ball for this. Let's let n1 be the set of all k and n such that ak is in the ball centered at x of radius 1. And this must be fine. There must be at least one x1 in f1 such that this set is infinite. Let's give ourselves a nice picture. So here is our set k, and here is our sequence. We're bouncing around, not sure which way we're going. Bouncing back and forth in k in x in all kinds of directions. However you want to do it. Now, and there's lots and lots of these AKs. There's infinitely many of them. They're a sequence. Now, the idea is there are finitely many points where we can draw. I'll make it a nice big ball for the sake of being able to see what's going on. Draw a ball around these finitely many points and contain in these finitely many balls all of x, which means we're containing all of the AKs. Now, if all of these balls had only finitely many points in them, union of finitely many points is finite, and that's no good. So one of these balls has to have infinitely many of the AKs in it. So let's suppose it's this one. Let's suppose this ball here is the one that contains infinitely many of the points. If there's more than one that contains infinitely many points, you just pick one, and then we'll let this thing be the point x1. And then we're going to let n1 is just the set of all of our indices such that an is in this ball. So if we've got A4 and let's say A17 and A23 here. So in this example, we've got A4 or A3, A17, A23 are all in the ball centered at x1 of radius 1. So we're going to say that 3, 4, 17, 23 are all in our set N1. And then we do that again. N1 is infinite. And we've done F1, so F2 is finite. It's the same picture with radius 1.5. So there is an x2 in F2 such that, let's call it N2. That's the set of all k in N1. Not all natural numbers, just the ones in N1, such that our point in our sequence point, our AK, is in the ball centered at x2 of radius, since it's F2 now 1/2. And then we can just proceed by induction. So suppose that some nk is infinite. Then fk plus 1 is finite. So there is an xk plus 1 in fk plus 1 such that nk plus 1, that's the set of all, maybe I shouldn't have used k, n in n sub k such that an is in the ball centered at xk plus 1 of radius 1 over k plus 1 is infinite. So we have constructed a sequence of points x, let's call them xn, and a sequence of infinite subsets of the natural numbers. We'll call that sequence is the NN, such that if k is in n sub n, then ak is in the ball centered at x sub n of radius 1 over n. Then we just pick n sub 1 in our first set, n sub 2 in n2, intersect all the natural numbers that are bigger than n1. And since n2 is infinite, there's definitely a point in that. So n sub k is in the set n sub k, and also bigger than k minus 1, since nk is infinite. We have that little nk must exist. And also, by the way we've constructed it, nk is a natural number, and nk is strictly bigger than nk minus 1. So a sub n sub k is a subsequence of the ANs. Now I claim this subsequence is Cauchy, and here's how we're going to prove this. We pick positive number epsilon. Let n be a natural number with n bigger than 2 over epsilon. So 1 over n is less than epsilon over 2. And let's let m and n be 2 natural numbers that are at least our capital N. Or, no, let's call them j and k, because we're dealing with our subsequence. Then a sub n sub k is in our set nk, but remember we said nk plus 1 is contained in nk, so nk is in n sub n. And similarly, anj is also in n sub n. So that means that ank and anj are both in the ball centered at our point xn of radius 1 over n. So by the triangle inequality, distance from ank to anj less than or equal to the distance to xn in the middle. Then just by the definition of open balls, these are both less than 1 over n, which is less than epsilon. So we've seen that for every epsilon, there's a natural number n such that if j and k are bigger than n, then the distance from ank to anj is less than epsilon. And that's precisely the definition of Cauchy. So our subsequence is Cauchy. Let's get back to compactness, and the next thing I want to do is prove a little lemma that will make checking to see whether something is compact a little bit easier. So we pick a metric space. And then the metric space is compact. Remember, you're compact if whenever you've got an open cover, there's some finite subcover. If you can cover the metric space with with a bunch of open sets, you can find finitely many of the open sets that still do the job. And what this lemma is going to say is you don't have to check all open covers. It's enough to check open covers that are just covering by balls. So let's state this open cover by balls condition. I'll put a star on it so we can refer back to that. Whenever there are numbers Rx greater than 0 for all x in K. This is essentially a function from K to the non-negative whole numbers, but I'm calling it R sub x instead of R or of x, such that K is contained in the union we have that K is contained in the union of finitely many of the balls for some finite number n and some finite set x1 up through xj, up through xn, sorry, of points in K. And of course, this condition here is sort of vacuous. If the R sub x's are positive, then of course K is going to be contained in this union of balls. Every x in K is in its own ball, but I wanted to state it at least at the start of the lemma so it would be clear how this is really just the definition of a compact applied to covers of balls. And the proof is not hard. If K is compact, then since this set of balls, each ball is, we saw that open balls are open sets, and this of course covers K. There is a finite subcover. Which we can write as the set of all balls centered at xj of radius rxj for j between 1 and n. And conversely, suppose star is true. And let's let G be a regular open cover. We're trying to show that K is compact, so we're trying to show that every open cover has a finite subcover. And then let's notice something. If X is in K, then because G is an open cover, then X has to be in one of the G's, one of the elements of our open cover. I'm going to name it G sub X for some G sub X in our open cover. And let's let R sub X be a positive number such that the ball centered at X of radius R sub X is contained in G. And we saw before that if G is an open set, early proposition in section 5.3, if G is an open set, every X in G, you can put a little ball around it and still be in G. Then by our assumption star, K is contained in the union of the balls centered at xj of radius rj, rxj. But that means that it's contained in the union of the gxj's, because these balls are contained in gxj's. So that means that the gxj's, each of them is a point in our set G, in our open cover G, and we've just seen that they cover G, so that is a finite subcover. So our open cover G has a finite subcover. We haven't used anything about G except that it is an open cover, so that means all open covers have finite subcovers, so K is compact. We've seen that if K is compact, then it is both complete and totally bounded. And we've seen that if K is totally bounded, then every sequence has a Cauchy subsequence. And if it's totally bounded and complete, then every sequence has a Cauchy and therefore convergent subsequence. Now we're going to prove the converse. Now we're going to prove essentially that K is compact if and only if it is both complete and totally bounded. And I am going to write that this way. And let's suppose that every sequence in K has a convergent subsequence. And the conclusion is that K is compact. And the proof at this point is not too terrible. We're going to use our lemma. So let's suppose that Rx is positive and defined for all x in K. And then we're going to try to come up with a finite subcover just in terms of balls. And then we're going to build a subsequence as follows. Let's let K1, we'll let that be K, and notice that this is not the empty set. I suppose if K is the empty metric space, which is technically a metric space, then that it's not true, but you can check that everything works for empty metric spaces. So let's just assume that K is not an empty metric space. And let's notice that the set of all of the radii for x in our K1 is not empty. Rx is positive. So let's let big R1, let's call that the supremum of the Rx, such that x is in K1, is positive or possibly there is no upper bound. We can write that as R1 equals infinity. But either it's a positive finite number or an infinite number. And if R1 is infinite, then there is an x1 in K1 such that R sub x1 is at least 1. If R1 is infinite, the supremum is infinity. There's no upper bound, so there is some Rx is bigger than anything you want. We'll just say bigger than 1 is enough. And if R1 is finite, but remember it's positive, then there is an x1 in K1 such that Rx1, it's at least 1/2 of R1. Because R1 is positive, it is strictly bigger than 1/2 R1. 1/2 R1 is not an upper bound for this set because the least upper bound is R1, so there must be some x in there with an Rx bigger than 1/2 R1. All right, so that's x1. Let's let K2 be K1, and we'll take away the ball centered at x1 of radius Rx1, which you can also write as K minus the union from J equals 1 to 1. It's a silly union now, but we're of course going to iterate this, and this will be less silly looking in a moment. And then if K2 is empty, then K is contained in a finite union of balls. So we have the conclusion we wanted, the thing which the previous lemma would let us use to say K is compact. Otherwise, we're going to pick an x2 in K2 such that Rx2 is at least 1, or let's write Rx2 is at least 1/2 the supremum of the Rx's such that x is in K2, or Rx2 is at least 1 if that supremum is indeed infinity. And then we're going to use induction to construct a sequence. We'll let Kn plus 1, that'll be Kn minus the ball centered at Xn of radius Rxn. That's K minus the union from J equals 1 up to N, ball centered at Xj of radius R, Xj. And if Kn is not the empty set, we'll pick, if Kn plus 1 is not the empty set, we'll pick Xn plus 1 in Kn plus 1 to satisfy r sub x sub n plus 1 is at least 1/2 the supremum over all the rx's. Or Rn plus 1, Rxn plus 1 is at least 1. So, two options. If Kn plus 1 is empty for some n, then that means that K is contained in the union of the balls. And if we could show that was always true, we would know that K is compact. And otherwise, we have constructed a sequence. If none of the KNs are empty, we don't have to stop, so we've got a sequence of XNs. It has a convergent subsequence by our assumption every sequence has a convergent subsequence, xnk from k equals 1 to infinity. And since this subsequence is convergent, xnk converges to x for some x in k. Now, r sub x is positive. This is the radius of the ball at the limit. And let's let k be bigger than j, and we'll assume that x sub n sub j, x sub n sub k both satisfy the distance from xnj to x is less than rx over 4. The distance from xnk to x is less than rx over 4, and there have to be k and j that this is true for by definition of convergent sequence. So that means that the distance from xnj to xnk by the triangle inequality, that's less than r sub x over 2. And x sub n sub k, since k is bigger than j, nk is strictly bigger than nj. So xnk is in our k sub n sub k. So that means it's not in any of the balls we threw out. In particular, xnk is not in the ball centered at xnj of radius r sub x sub n sub j. I'm going to just call that r sub j. I do not want to have to write 4 subscripts any more than I absolutely have to. So we have that Rx over 2 is greater than the distance from xnj to xnk, which is at least r sub j, which is in turn at least 1/2 the supremum of all ry, such that y is in k sub n sub j. That's how we defined x sub n sub j. So r sub x over half of r sub x is at least half this supremum, is bigger than half this supremum. That means Rx can't be in this set. So X must be in K sub N sub J, must not be in K sub N sub J. So that means X is in the union of the balls centered at the XLs of radius RXL. This is an open set, so there is some positive epsilon contained in this union. That's an NG minus 1. And then now all we have to do is notice that there is a positive m bigger than j, such that the distance from x sub n sub m to x is less than epsilon by definition of convergent sequence. So you can always find an m big enough such that you're within epsilon of your limit. So that means x sub n sub m is contained in this union. And this is a contradiction. That because remember XNM, it's specifically picked not to be in this union of balls. So that means that K has to be in, we have to stop eventually. Because we can't because if we didn't have to stop eventually, we'd come up with a sequence and then we'd get a contradiction. So that means K is compact. Let's outline what we've proven so far. So we're going to let KD be a metric space. Then here are some concepts. So the first is KD is compact. And we've seen that if KD is compact, then KD is complete. And also that KD is totally bounded. And if KD is totally bounded, then we have that every sequence in the space is going to have a convergent subsequence. Sorry, a Cauchy subsequence. But let me point out, if you put these things together, you do get, if you're both complete and totally bounded, then every sequence has a Cauchy and therefore convergent subsequence. And we have just seen that if every sequence has a convergent subsequence, then K is compact. So we've got these three ideas. K is compact. Which notice is showing up twice. And we've got this other idea that every sequence in K has a convergent subsequence. And we've got this pair of ideas that K is complete and K is totally bounded. And if you have both of those, well, the idea here is that any one of these three things implies the others. One of the three things is a pair. We're also going to see that there's an implication back this way. If every sequence has a Cauchy subsequence, then your set is totally bounded. That was originally going to be part of this video, but there wasn't enough time, so you'll see this implication in the next video. But here we've got two conditions that are equivalent to being compact that might be useful to you if you ever need to prove something is compact.